Hello everyone, welcome to the course on measurement and instrumentation, and this is the 7th week of our discussion and this is the second lecture of this particular week. Okay, and we are discussing about transducers. I have given you a brief overview of the transducers in the first class. Okay, and we have seen in the previous lecture that when choosing a transducer for any application, okay, three characteristics we have to take into account. The three characteristics that we discussed were the input characteristic of the transducer, the output characteristic as well as its transfer characteristic. Okay. We were discussing the transfer characteristics of the transducer, which required the attention of three separate elements. First was the transfer function, second is the error, and third is the response of the transducer to the environmental factors. Okay. So, today let us see the second element, that is the error. We discussed the transfer function in our first lecture, right. So, now let us discuss error in the transducers. We have discussed errors in general in our first module. Okay. However, we will extend our discussion here, okay, so that we understand exactly the errors that is specific to the transducers. Okay. So, when I say error in the transducer, this error occurs because they do not follow the input output relationship or the ideal transfer function of the transducer. Okay. So, we have seen that if I have to write the transfer function of the transducer, usually it is written in the form of your output by input. Okay. Or if I say the output was given as in generalized Q naught is equal to FQI, where QI was the input function or the output was a function of your input. Okay, this is how we have discussed the transfer function. Now, if there is any deviation of the transducer or the transfer function of the transducer from this particular equation, it means that there is certain error from which this transducer is suffering. Okay. The error in a transducer can be split into three different components. Okay. And these three different components are the scale error, dynamic error, and the error on account of noise or because of certain drift. Okay. So, again the scale error can again be classified into four different errors: zero error, sensitivity error, non-conformity error, and the hysteresis. Okay. So, let us see all of these four different errors in brief, so that we understand how they are going to affect the transducers that we are going to discuss from the next lecture. Okay. So, first scale error is the zero error. Okay. And in the zero error happens when you have a practical and theoretical curve of input versus output, something like this. Okay. If you see this very carefully, you can notice a pattern that the output here is deviating from the correct value by certain constant. Okay. Like this constant here is this epsilon. Okay. So, if you see at any point, okay, at any point in this say output versus input curve, okay, you will find that there is a deviation with a constant amount. Okay. Now, this deviation remains the same across the entire operating range of the transducer or in the entire span of the transducer. Okay. Now, the error, if you see, is independent of the input magnitude, be it say 2, be it 4, 6, whatever, you will have this error. Now, the second scale error is the sensitivity error. Okay. And sensitivity error occurs when the observed output deviates from the correct value by a constant factor, something like this. So, you have this theoretical curve, okay, of Q naught, okay, and then you have a practical curve. If you see, this has scaled up by a constant K. Now, earlier you expected Q naught, now your practical curve is suggesting KQ naught. Okay. Now, the correct output is now scaled by a value, say constant value by K over the entire range. Okay. Here the K is the constant. In this case, we call that there is a sensitivity error. Okay. Now, the third error is the non-conformity. So, the experimentally obtained transfer function differs from the theoretical transfer function at any point. practically it happens. Okay. Now this deviation occurs for nearly every input value, and you cannot expect that in this particular range of input you have deviation, and in this particular range it is not. This deviation occurs nearly at every input value. Now it indicates a consistent mismatch between the expected and actual system behavior. Okay. Now this dotted was, say, your theoretical data. Okay. This dotted line is showing your theoretical data, and your practical curve is something like this. It is not, say, following this or not getting conformal over the theoretical curve. Now it indicates a consistent mismatch between a expected value. Expected value is nothing but the theoretical data and the actual system, which is basically the practical curve. So in the special case of a theoretical linear relationship between input and output quantities, this error can also be called as non-linearity error, because the relationship between input and output was linear, and any deviation from that is, of course, can be called as the non-linearity, or sometimes we also call it non-linear distortion. Fine. So the fourth kind of scale error is the hysteresis. We have discussed hysteresis in detail in our initial modules. Okay. All transducers have a certain amount of hysteresis present in their output. The output of a transducer depends not only on the present input but also on the previously applied input, and that is how we understood a hysteresis. And a typical data for hysteresis or typical curve for a hysteresis is shown here. So you increased the input from initial point to, say, final point and in a span, and then you decreased it, and ideally they should coincide. However, it is not coinciding, means that there is certain hysteresis present. Now, when the same input value is applied, the output can vary based on whether the input is increasing or decreasing. Okay. Sometime you may also get it like this, okay, depending on, and sometime it may not be like this. Sometime you may also, we have seen this with a certain example, that when we increased say input from certain value to maximum value, and in, say, higher concentration range it was coinciding, but then we had hysteresis. So you can say in these cases that in higher concentration or, say, higher input range, okay, you had nearly no hysteresis, while the hysteresis is more prominent in the lower regime or lower input regime, right. So these were different scale errors. Okay. Then second thing that we wanted to discuss is the errors due to noises and drifts. Please note that there are differences between them. Okay. So the difference between noise and drift is that noise consists of a signal of a random amplitude and random frequency, while drift is a slow change with time. Okay. So slow change in the baseline or slow change in the output, okay, they both are actually similar. If there is a slow change in the drift in the baseline itself, okay, there will be, of course, change in the output as well. Okay. The magnitude of the noise and drift is normally independent of the magnitude of the input signal. Then we have another error, which is the dynamic error. Okay. And dynamic error occurs when the input quantity changes with time. The output cannot respond instantaneously to the input. As a result, the output follow the input. However, there is a time lag. Okay. Of course, I am not telling that output is not following the input, but it is following with certain time lag. And this leads to a temporary mismatch between the actual input and the measured output. And this is how a dynamic error looks like. Now, consider series RC circuit, which is subjected to a step input of certain magnitude, say E. Now, when the step input is applied, the capacitor begin to charge through the resistor. So you have a series combination of R and C. So this is your C and this is your R, and you have applied a step input, okay, of magnitude E. Okay. Now, when the step input is applied, the capacitor begins to charge through this particular resistor, and the voltage across the capacitor increases gradually rather than instantaneously. We know that capacitor charges gradually, right. So after a time t, the capacitor voltage is determined by charging behavior of this particular RC circuit. Now the voltage across capacitor can be given as, say, E minus E into e to the power t minus t by tau, or the voltage across capacitor EC can be given as E bracket 1 minus this exponential minus t by tau, where this tau is nothing but the time constant of the system, okay, and this is given as RC. So this tau is equal to RC. Now if you have this kind of system, the dynamic, or sometimes also known as measurement error, can be given as the EMT, I mean this value, this error, ideally it should have coincide, but it is not, okay. So EMT is given as E minus the voltage across the capacitor, okay, and we have seen that voltage across capacitor is E into 1 minus e to the power minus t by tau. So it is actually E minus E into 1 minus e power minus t by tau, okay. So it is actually E into e power minus t by tau, right. So if you want to calculate the steady state error, okay, it will be just limit, say, t tends to 0 and the dynamic error, right. By this you can also calculate the steady state error. Fine. So this is the dynamic error, sometime also known as the measurement error, okay. Now dynamic error can be minimized by using a system with a small time constant. So a smaller time constant allows the system to respond more quickly to any change in the input. Dynamic error varies with time and therefore is of course time dependent, and as more time passes after the input is applied, the dynamic error gradually decreases, okay. With time actually it will decrease. Eventually the system output approaches the true input value, and that is how the steady state error is calculated. Fine. So this is the generic, errors in a transducer, but we also have to see other ways that how errors can arise in a transducer, particularly from the user point of view, okay. Sometime we also want to see that how the transducer behaves with frequency, okay, and that's where we have to understand the errors due to changes in the frequency for the transducer, or changes in the frequency of the operation of the transducer basically, okay. So two specifications that describe the response of a transducer to a variable frequency, say a sine wave input, are the frequency response and high frequency cutoff of the transducer, okay. So frequency response, we have to understand, you might have seen this frequency response for transistors, for amplifiers and so on, and this is also very similar to what you have seen, okay. We are considering of course a sine wave right now, okay. So for a linear transducer, of course a sine wave input should yield a sine wave output only, because the response is linear, okay. Now as the frequency of the sine wave input is increased, the transducer is required to respond more and more quickly, okay, and sometime it may not happen, because ultimately beyond a particular frequency the transducer can no longer respond as rapidly as the sinusoidal input is changing, okay. So the output of the transducer becomes smaller, and you will also see that there is a phase shift between the input and output, and then this phase shift will increase and increase when you are increasing the input frequency, okay. Now as the frequency increases, the output of the transducer falls, okay, and this roll off of the amplitude of the output with an increase in input frequency is known as the frequency response. And please note that right now I am talking in terms of amplitude only, but then frequency response also covers the changes in phase and other things, okay. So overall change in the response pattern of the transducer, we would say rather, okay. So let's see this with one example, okay. Now in this case the vertical axis is the gain of the transducer, and this may be simply the output to input ratio. Usually it is denoted like this. However, the gain is specified in terms of decibel. Okay. And if you know the concept of decibel in case of amplifier or other transistors, okay, gain in dB is usually represented as like this. So you have 20 log output by input, and for our case we are taking Q naught as the output. We have seen that Q naught is equal to f function of Qi. This is what function we are considering for throughout this transducer module. Okay. So the gain in dB is something, say 20 log Q naught by Qi. Okay. Now the horizontal axis represents the frequency and is plotted on a logarithmic scale in order to cover a wide range of the frequency, and that's how it is shown over here. Okay. Now the higher frequency, which is known as cutoff frequency, FH, is the frequency at which the transducer's gain has fallen to 0.707 of the value it has at its stable low frequency operation. Okay. So the high frequency cutoff can be related to the rise time by the relationship of like this. So you have rise time equal to 0.35 divided by the higher cutoff frequency FH. So these two specification that we have seen for the errors or for quantifying the errors due to change in the frequency, that are the frequency response and high frequency cutoff. Okay. So now if the vertical axis is scaled in dB, this higher cutoff frequency occurs when the gain has decreased by -3 dB. Okay. Now this figure shows the low frequency gain is say 20 dB, but drops off to say 17 dB, means that there is a drop by 3 dB at a frequency of say in this case say 4 kilohertz. Okay. Therefore, we can simply say that the high frequency cutoff takes place at 4 kilohertz for this particular case. Okay. Depending on what kind of transducer it is, you may have a variable higher cutoff frequency, but it is useful if your operation requires a frequency consideration. All right. Then another characteristics that end user should see for a transducer is the output characteristic of the transducer. Okay. Now, three conditions in the output characteristic which should be considered are the type of electrical output, because you have to take care of the subsequent steps, because transducer output may not be the end goal of the user. Okay. You may want to cascade it with certain amplifier or something for the subsequent stages. Okay. Now, second thing that you have to take care is the output impedance, and the third is the useful output range. Okay. So you have to consider all these three output characteristics while considering a transducer. Okay. Now let us see the first one, which is the type of electrical output. Okay. The transducers can produce different type of outputs. You can get output in the form of voltage, you can get output in the form of current, you can also get output in the form of impedance, and so on. Okay. Or you can also get time varying signal based on all these three quantities. Okay. Now these output represent the measured physical parameter in electrical form. However, the generated output may not always be suitable for the next stages of the instrumentation system. Therefore, you have to be careful that what output signal you require for say if you have a ADC, you have a DAC, or whatever stage it has, you have to take care of that. Otherwise, you may have to add one more step in between to have a subsequent stage conversion. Say you may require a stage to convert say voltage to frequency, or voltage to charge, or charge to voltage, depending on what is the next stage of your instrumentation system. Okay. Now second characteristic is the output impedance. Okay. The output impedance, usually denoted as Z naught, of a transducer determines to the extent the subsequent stages of the instrument is loaded. Okay. So ideally the value of output impedance should be 0 if no loading effect are there on the subsequent stages, but it is not always 0. Okay. Because this cannot be made 0 in practical case, so its value should be kept as low as possible to minimize the loading effect. we know that this is a characteristic of any transducer or any system, that you want the input impedance to be maximum while output impedance should be minimum. Input impedance we want maximum because it should not load the system in which it is getting attached, right. The output impedance determines the amount of power that can be transferred to the succeeding stages of the instrumentation system for a given output signal level, all right. So, if the output impedance is low compared to the load impedance of the successive stage, the transducer has the characteristic of a constant voltage source, provided the output of the transducer is a voltage. It can be called a constant current source if the output is current. Okay. In case of the forward impedance is low as compared with the output impedance of the transducer, it behaves as a constant current source. Okay. So, if you talk about a constant voltage source, as the name suggests, output voltage is constant and it is independent of the load connected to the source, and same you can say about the constant current source. Okay. So, coming back to the constant voltage source, even there is a current drawn from the source, the output should be independent of all these factors, it should be constant. Okay. However, we know that in practical sense it is not possible. You will have voltage varying at the output, okay, and it must actually vary with time if it represents a signal which is true of the transducer, since their output is dependent upon the input signal which vary with the time. So, if a constant voltage source, say having a voltage of E, is applied across a resistor R, the current is E by R as shown over here. Okay. Now, a constant voltage source in a strict sense does not exist, as we have mentioned earlier. The output voltage will always vary with the current drawn by the system, and the output looks something like this, right. This is because a practical voltage source has an internal resistance of itself. Okay. Say internal resistance is R naught. Due to this, the voltage across the load resistance EL decreases with the increase of current or decreases of load resistance RL. Okay. So, let us consider this figure which shows a practical voltage source like this, which consists of voltage source E, and there is an internal resistance R naught in series with this battery, and it is connected across a load RL. Okay. Now, current in this circuit can be simply calculated as E by R naught plus RL, or voltage across EL. The load can be this voltage EL can be given as E into RL by R naught plus RL, and if you simplify, it is E by 1 plus R naught by RL, right. So, this EL is given as E by 1 plus R naught by RL. So, in case the internal resistance or the output resistance of the battery R naught of the source is much smaller than the load resistance, for instance R naught is 1 kilo ohm while RL is in range of certain mega ohm, then the ratio of R naught by RL is very small as compared with the unity, and hence the voltage across. So, if this term is very small, you can say that this EL is equal to E, and the current that is flowing is E by RL. Okay. Thus, the voltage across the load is constant and the current is independent of the internal resistance R naught of the source. So, the source behaves as a constant voltage source as indicated here in the region N, right. However, of course, these conditions has to be matched, and for that you should know the internal resistance of the battery itself or the source itself. Okay. Similar consideration you may have for a constant current source. Okay. And I think with this we have a basic understanding of how to choose a transducer as an end user. Okay. We will continue our discussion on the transducer in our next lecture. There we will mostly talk about the practical transducers. Till now we have seen just characteristics of the transducers. In the next class, maybe we will start our discussion of our transducers, and maybe we will start with the simple strain gauge kind of transducers. Okay. So, thank you for attending this lecture.